Okay, hello. This is Zhang from University of Bath. Today, I will present our work on strategic agent-based equilibrium models for urban mobility, with a particular focus on what we call the traffic filter location problem. The motivation for this work comes from recent changes in urban transport policy, where planners increasingly rely on relatively simple restrictions, such as basket, to shape travel behavior. What is particularly striking about this policy trend is how modest this intervention appears at first glance. A traffic filter is often nothing more than a restriction on a single road segment. There's no pricing, no new infrastructures, and no direct control over travelers' decisions. And yet, once such a restriction is introduced, the entire system begins to react. The goal of this work is to provide a formal equilibrium framework that allows us to reason rigorously about the effect of these interventions, and in particular, about where they should be placed in a network. Rather than asking whether traffic filters are good or bad in general, we ask a more precise question. Given strategic travelers and congestion effect, where does a filter do the most good? Urban planning is gradually shifting away from car-centric design. This shift is driven by several factors, including quality of life in dense urban environment, environmental sustainability, and the recognition that existing infrastructure must be used more efficiently rather than continuously expanded. Importantly, in many cities, the objective is not to eliminate private vehicles entirely. Instead, the goal is to reduce the dominance and rebalance the system so that public transport becomes a more attractive and competitive option. This represents a fundamental change in how success is defined in transport planning. From a modeling perspective, this shift has major implications. If policies are intended to influence individual behavior, then we need models that explicitly capture behavioral responses to interventions. Models that assume the fixed demand or centrally controlled traffic flows are no longer sufficient for answering this kind of questions the planners are asking now. Traffic filters, also known as modal filters or basket, restrict which modes of transport can use. Typically, they prevent private vehicles while allowing buses to pass, and sometimes other modes such as bicycles. These measures are attractive because they are cheap, easy to implement, and highly flexible. Many cities deploy them increasingly, monitor outcomes, and adjust them over time. As a result, they are increasingly used in practice across the UK and internationally. Despite the growing popularity, there has been relatively little theoretical study of the network-wide effects, especially in models that account for agent behavior and mode choice. Much of the existing work either focuses on local effects or assumes that travelers respond passively rather than strategically. We compare different policy measures in terms of cost and impact. Large infrastructures, project and tolling systems are expensive, slow to deploy, and often politically sensitive. Dedicated bus lanes sit somewhere in the middle, requiring physical space and long-term commitment. Traffic filters stand out because they are low-cost interventions. yet they can strongly affect the relative utilities of private and public transport. Rather than adding incentives or change fees, they remove specific options from the choice set. This leads to an important and somewhat counterintuitive question. Can removing options actually improve equilibrium outcomes in a traffic network? Or does it simply push congestion elsewhere? Answering this question requires a careful equilibrium analysis rather than intuitive alone. The structure of our work is as follows. We first formulate the traffic filter location problem mathematically, making explicit what the planner controls and how agents respond. We then introduce a multimodal equilibrium model that incorporates stochastic utilities and elastic demand. This allows agents to choose route, choose modes, or decide not to travel at all. We prove that an equilibrium always exists under this model, which is an essential theoretical foundation. Finally, we run experiments to study how traffic filters affect congestion, modal split, and travel demand. Together, these components provide a foundation for future work on both theory and applications. To motivate the model, we begin with the basic inputs. We represent the traffic system as a network topology modeled as a graph. Nodes represent nodes corresponds to locations or centroids, and the edges correspond to road segments. We also specify demand in the road in the form of origin destination paths. These demands represent latent demand, meaning the number of agents who would like to travel between locations before considering congestion, travel times, or other cost. This distinction between latent demand and realistic demand is important. A policy intervention might reduce congestion, but also discourage some agents from traveling, or it may shift agents between modes while keeping total demand roughly constant. Each agent in the network is associated with a latent function, which maps traffic flow to travel time. These functions are assumed to be continuous and increasing, capturing congestion effects where higher flow leads to longer travel time. Latency functions are the mechanisms through which individual routing decisions interact. When many agents choose similar routes, congestion increases, which rise travel times and alters incentive for everyone else. This feedback between individual behavior and system-level outcome is what generates equilibrium behavior in transportation networks, and it is central to our modeling approach. Agents are modeled non-atomically, meaning we work with flows rather than discrete individuals. Each agent chooses a complete path between the origin and destination. At equilibrium, all paths that are used have equal and minimum perceived cost. No agent can improve the outcome by unilaterally changing routes. This corresponds to the standard user equilibrium formulation. It captures the idea that inefficiencies can arise even when all agents behave rationally and selfishly, making it a natural baseline for studying policy interventions. We augment this classic model in two key ways. First, We introduce multiple mode of transport, focusing on cars and buses. Agents now choose not only routes, but also how they travel. Second, we incorporate stochastic utilities and elastic demand. Stochastic utilities capture heterogeneity in agent preferences that cannot be explained by observable factors alone. Elastic demand allows agents to opt out of traveling if travel becomes unattractive. These features are essential for modeling traffic filters. Without them, filters would simply force rerouting. With them, we can capture model switching, changes in demand, and more subtle behavior responses. We introduce the core planning question. Where should the traffic filters be placed? In our model, placing a traffic filter corresponds to removing an edge from the car network while leaving it available to buses. This intervention directly changes the feasible routes for cars. Although the intervention is local, its consequences are global. Agent reroute, congestion shift, and model utilities change throughout the network. This is why local reasoning alone is insufficient for solving the problem. The traffic filter location problem has a bi-level structure. The outer problem is a planner's decision. Choose which edge to restrict. The inner problem is behavioral, computing new equilibrium that results from the restriction. Solving the outer problem therefore requires repeatedly solving the inner equilibrium problem. This structure mirrors real-world planning. A planner makes a decision and travelers respond strategically. Understanding the quality of that decision requires predicting the full equilibrium response, not just the immediate effects. Model choice is modeled using random utility theory. Each agent associates a utility with traveling by car, by bus, or not traveling. Utilities consist of a deterministic component, which depends on travel time and fixed cost, and a random component, which capture unobserved preferences. We then aggregate our agent model. A model shares emerge as probability derived from these utilities. This provides a principled link between individual level decision making and the aggregate travel patterns. To compute the equilibrium, we adapt a two-level algorithm based on column generation and path swapping. Excuse me. The algorithm starts with a small set of candidate paths and iteratively adds better ones. At the same time, flows are redistributed across paths and modes until no agent has an incentive to change behavior. Although computationally expensive, this approach avoids enumerating all possible paths upfront and allows us to compute equilibria for networks of meaningful size. Our main theoretical result is a proof of equilibrium existence. The key idea is to show that the mapping from demands to travel time is continuous, and that mapping from travel time to induced demands is also continuous. By composing these mappings, we obtain a continuous function or a compact set. A fixed point argument then guarantees the existence of an equilibrium under very weak assumptions. This result ensures that the equilibrium is a genuine property of the model rather than an artifact of the numerical method used to compute it. We evaluate the model using two small syntactic networks and a large real-world network from Anaheim. For each network, we compute a baseline equilibrium. We then remove each feasible edge from the car network in turn, recompute the equilibrium, and measure the effect on several objective functions. The exhaustive approach allows us to systematically compare different traffic filter placement and assess the impact across multiple dimensions. The main findings are as follows. We found out that removing a single edge almost always improves all of our objectives. Congestion decreases, bus usage increases, and the fraction of agents who choose to travel is maintained or slightly increased. Interestingly, these improvements are stronger when agents have a stronger preferences for cars. Higher baseline congestion appears to amplify the effect of the filter, making public transport relatively more attractive. This behavior resembles an inverse brass type effect, where removing capacity improves overall system performance. Finally, we outline directions for future work. These include developing heuristics to identify good filter locations without exhaustive search, extending the model to multiple simultaneous filters, and incorporating richer behavior and dynamic elements. More broadly, we believe this framework provides a solid foundation for future theoretical and applied research on sustainable urban transport. Our hope is that it can help bridge rigorous equilibrium modeling and the real-world policy design. That concludes my talk. Thank you for your attention.